Okay, we're going to do the third and last part of today's lecture. We're going to talk about potential divider circuits here. Right, so previously we already talked about your conservation of charge, conservation of energy. So that will give you your two formulas, and then you talk about resistance in parallel circuits and then resistance in series circuit as well. So we're going to move on to some of the application type. So this is the potential divider circuit, right? So what is a potential divider circuit? Alright, so what we're going to do is that we're going to set up a circuit this way, which looks very similar to our usual series resistance circuit. So one EMF source with no internal resistance for now, and then you will have it going through resistor 1 and resistor 2. So that's R1 and R2, and you have the same current throughout. Okay, but what I'm going to do now is I'm going to tap across this first resistor here. So right now, remember this cable here, this wire has no resistance at all. So whatever potential that is from here will be the potential as well. Okay, so this end is at a higher potential than this end, because as your current goes through R1, you will drop some of its energy. You convert some electric energy to your non-electrical forms, and then you will have a lower potential as a result. And then come back, drop to R2, you go down by more, and then eventually you go back down to zero here lah, right? So this is how it works. Okay, some of the potential is dropped across your first resistor, some of the potential is dropped across the second resistor. Okay, we're gonna see how we're going to calculate all these things. Right? So now again the same diagram. Okay, then we will do the calculation. First thing first, we know that current is the same throughout the cell and the resistor. So I is a constant throughout here. Okay, once you know that, you can do I equals to V in over R1 plus R2. So this is basically to find the current based on the total resistance of R1 and R2. Okay, and V in here, for this case, V in is actually just equals to your EMF lah, right? Or you just use V in, okay? So we know that your V out, the output here, this is basically the potential drop across R1, and it can be obtained by I times R1. So I get V, if I sub I as V in over R1 plus R2, I get this form. I'm going to make one more rearrangement. I'll get V out equals to R1 over R1 plus R2 times V in. So basically I just swap the position for this R1 and V in. And what's the implication of this? You can see right now, this value here will definitely be less than 1. R1 over R1 plus 2 will be less than 1, provided R1 and R2 are non-zero. Okay, and so this is a fraction. That means your potential difference across your V out, right, will be proportional to the proportion of R1 over R1 plus R2. Alright, so let's say they are equal, but let's say R1 equals R2 equals to 5 ohms. So this will be 5 over 5 plus 5, you get half. And then V will be half of V in. Okay, and if it's a lower value, say like 1 and 9, so there'll be 1 over 1 plus 9, you get 110, which is 10%. Okay, so that means if I'm able to do something to it, let's say I make one of these resistors become a variable resistor here. Okay, like this. Okay, I can do things to affect, I can adjust this resistance value such that it affects the proportion of R1's resistance compared to the total resistance, right? So by doing that, right, I'm able to adjust my reading to get different, I can adjust my resistance value here to get different V outputs here, depending on what I want. Okay, so let's look at one of these questions first. This is an application question. So in the circuit shown, resistors X and Y, each of them have each of resistors R are connected to a 6-volt battery of negligible internal resistance. When a voltmeter also of resistance R is connected across Y, what is the reading of this voltmeter? So remember in the ideal case, right? You might have learned this at secondary school. Your voltmeter is supposed to have infinite resistance, right? The reason for this is such that as the current comes through here, once it comes to this path, I don't want the current to go through my voltmeter. Okay, I want all the current to go through here. So this voltmeter will give me an accurate reading of the potential drop here. Okay, it can only do so if none of the current passes through the voltmeter. All the current passes through your actual resistor here. Okay, but in reality, right, it's very hard. Your voltmeter will have some finite value of resistance. So the way to do this is to basically imagine that there is another another resistor here. Let me just quickly draw one resistor here like this. Okay, that's just ugly resistor. Okay, and this is the resistance of the voltmeter. Okay, I can't write this well, but yeah, this is the resistance of your voltmeter. Okay, and this value here is equals to R as well. Okay, so once you have that, right, then now your voltmeter becomes an infinite resistance voltmeter lah. Or if you don't want to, you can just assume that this is just tap across two leads, the A and B lead just now. Okay, sorry. All right. So how do we do this now? We basically combine our voltmeter's resistance into Y here, because this is not in parallel. So I'll form a combined resistance of Y and the voltmeter's resistance, and it's R over 2. The reason it's R over 2 is because across AB, right, you have 1 over R, this original 1 over R, plus this 1 over R as well. And this is equals to 1 over RAB, so RAB equals to half, or half of R. Okay, and once you have that, right, you realize that now this is R over 2 and this is R. You are making a potential divider across the second resistor here. So if you take the ratio, this is R over 2 over R over 2 plus R. Okay, so R over 2 over R over 2 plus R multiplied by the EMF source, which is your V input here. So that's your 6 volts. So this is equals to 1/3. It will be R over 2 plus 3R over 2, so it's 1/3. Right, and so therefore your potential drop across here is 2 volts. Okay, so this means that at the starting here, let me get a pen again. At the starting here, this is 6 volts. Okay, so that means this end is also at, this end is at 6, this end is at 0. Alright, then this end is at 6. Okay, we know that this drop is a 2 volt drop. This is a 2 volt drop. Okay, so if this is 0 as well, okay, to drop from something to 0, drop by 2 drop by 2 from something to 0, that means this is 2. Okay, that means this drop from across X, right, will be a drop of 4 volts. Okay, yep, so that's how the potential divider concept works. Alright, okay, next we have this circuit here. Internal resistance of the 12 volt battery is negligible, so this is not internal resistance, this is just a 10 ohm resistor connected in series to this parallel branch here. Okay, determine the value of the current I. Okay, then you have second part, we talk about that later. So for this, right, we need to combine these two first. 6 and 3 ohms combine in parallel first. Once you combine in parallel, right, it becomes a single resistor. Then you notice that now, oh, this is a potential divider concept. Then your combined resistor, let's just quickly combine them together. I'm just going to do a giant box. Okay, just going to treat this as a combined resistor. Okay, giant box like that. Okay, so basically your circuit becomes something. Okay, I don't have space to draw. I realize if I draw it here, it will interfere with my diagram. Okay, so it becomes just a path like that. Okay, combine them together. Alright, so to do that, let's see what I can do. First thing first, across AB, we combine the 6 and 3 in parallel first. 1 over 6 plus 1 over 3, then inverse the answer, you get 2 ohms. Okay, so this 2 ohms is now in, let me label it for you, this 2 ohms effective, okay, is in series with the 10 ohms. Okay, so if it's series 10 ohms, you can use potential divider concept. Okay, so to find VAB, you will just take the ratio, of this resistance over the total resistance. So this will be 2 plus 2 plus 10. Okay, 2 over 2 plus 10. So 2 over 12. I get 2 volts nicely. Alright. Okay, so right now we are supposed to find current. So we know our potential drop here. We know this resistance. We can find the current now. So we take VAB divided by 6 volts. Okay, why am I using 6 volts? Because what's my total resistance? Okay, because my total resistance, did I make a mistake here somewhere? Let me check. Okay, yeah, because I can just take for one path here. Alright, because I want to find current through AB, the original 6 ohm. So the PD across AB is 2 volts here. It's also 2 volts here, so I just use for this one. Okay, so I just take 2 volts divided by 6 ohm, I get 0.33 ampere. Okay, next, Now we're going to add a 1 ohm internal resistance. I've added it in blue color over here, this one. So how will it affect the current reading? So we can do the same calculation. The first part is still the same. The add up the 6 ohm and 3 ohm. Okay, so then now your VAB will change slightly. Because your VAB now, this will be, remember your RAB is still 2 ohms, but now instead of adding 2 and 10, I'm adding 2 and 10 and a 1 as well to cater for the internal resistance. So now your VAB is 1 over 8.846 volts. Okay, then you just take the same method, find your current. I equals to VAB over 6, because this path has 6 ohms of resistance, and you get 1.846 divided by 6, you get 0.31 ampere. Okay, be careful not to use 3 ohms here, because this current going through the top branch is not the same as the current going through the second branch here, right? Okay, next we have this setup here. Calculate potential at point B for the circuit as shown below. Okay, so here you can see that there are 2 resistors, so do you know that there's a potential divider here? Okay, and then there's a point mark B in the middle. Alright, and you can see that this point A starts at positive 3 volts, and this point C is at negative 15 volts. So that means the potential drop across here is equals to 18 volts. Okay, let me just try to write it. 18 volts. Okay, 18 volts of drop. Okay, so when it drops, right, that means from A drops to B, this drop, and B to C, this drop together, it must give you 18 volts. Okay, how far it drops will depend on the potential difference. So what we can do is that we can work out some stuff first. Let's work out VAC. This one I've already done above. So VAC is equals to potential difference between A and C is potential A minus potential of C. So 3 minus negative 15, that's a difference of 18 volts. That's fine. Next, we use potential divider concept for our resistors. Okay, we want to find VAB, potential drop across here from A to B. So I'll take the ratio of this resistance over the total resistance. So this will be 200 times 10 power 3 over 200 times 10 power 3 plus 1 times 10 power 6 multiplied by 18. And this will give me 3 volts. Okay, so this means that from A to B, it has to drop by 3 volts. Okay, let me write it down. Okay, that means the remaining 15 volts is dropped here. Okay, this is 15 volts. Try to write it. Okay, 15 volts. Okay, so now you know that from positive 3 volts, you're going to drop 3 volts. So this one will be 3 minus 3, you get 0 volts. Okay, then we check 0 drop by 15 volts, I'll get exactly negative 15. Right? So VAB equals to VA minus VB. So 3 equals to 3 minus VB. So I get VB equals to 0. Alright? Yep, so that's it for this example 6. Okay, and this is the end of lecture 1. Please go on to complete the checkpoint for lecture 1 before taking a break for the rest of the day. Alright, thank you.